Hello everyone. Let's now look at material strength testing. This testing determines a material or component's ability to withstand forces such as tension, compression, bending, shear, torsion and impact without failing. It tells us how much load a material can handle, how it deforms, and when it yields or breaks. The goal is to ensure that materials meet design and safety standards, while also guiding material selection and quality control. This is especially important in industries like automotive, aerospace and heavy machinery, where reliability and performance are critical. In short, it's about making sure materials not only pass specifications on paper, but also perform consistently under real-world stresses. It's all about making sure a material or component can handle the loads, forces and stresses it will face in real life, without cracking, bending or failing. This keeps products safe and reliable, especially in industries where failure is not an option. Strength testing also guides material selection, so you don't end up over-designing, wasting money, or under-designing, risking failure. It spots defects like porosity or heat treatment errors early, ensuring consistent production quality. On top of that, it confirms your design meets global standards such as ASTM, ISO or IS, essential for certifications and regulatory approvals. Plus, the data helps predict fatigue life, prevent breakdowns, and plan maintenance better. Bottom line, it saves costs, prevents recalls, and builds trust in your product's performance. Material strength testing is vital across industries, from cars and aircraft to buildings, machinery, and electronics, ensuring safety, durability, and performance in every application. These are the major material testing methods we use, from tensile and compression testing to hardness, fatigue and fracture toughness evaluation. Each method serves a unique purpose in determining material performance. We'll go through each of these in detail in the upcoming slides. Let's start with tensile testing. This method evaluates a material's resistance to uniaxial pulling force, in other words, how much load it can handle before it breaks. The specimen is usually shaped like a standard dog bone or a flat strip, as defined in ASTM and ISO standards. In the test setup, we place the specimen in a universal testing machine with proper axial alignment. The machine applies a controlled loading rate. For metals, this is usually between 0.015 to 0.05 mm per minute strain rate, while for non-metals, it uses a constant crosshead speed. Now, if you look at the graph on the right, you can see the engineering stress versus engineering strain curve. Initially, the curve rises linearly. That's the elastic region, where the material returns to its original shape after the load is removed. The proportional limit marks the end of that linear behaviour. As we go further, we reach the yield strength, where permanent deformation starts. The peak of the curve is the ultimate tensile strength, the maximum stress the material can handle. After that, the curve drops as the material necks and finally fractures. The key outputs from this test are ultimate tensile strength, yield strength, elongation percentage, and modulus of elasticity. Next, we have compression testing. Here, instead of pulling, we apply a uniaxial compressive force to see how the material withstands crushing or buckling. The specimen is usually cylindrical or prismatic, with ends that are flat and parallel to ensure even loading. In the test setup, we place the specimen between two hardened compression platens inside the universal testing machine. The loading rate varies. For metals, it's typically 0.5 to 1 mm per minute, and for plastics it can go up to 10 mm per minute based on standards. Looking at the graph below, you can see stress increasing as the specimen shortens. The curve rises until it reaches the compressive yield point, where permanent deformation begins. Beyond that, the material might either densify or start to fail. The main outputs here include compressive strength, modulus, yield point in compression, and the percentage deformation at failure. Flexural testing. In a flexural test, we measure how much bending strength and stiffness a material has. We usually do this with a 3-point or 4-point bending setup, where the specimen, either rectangular or cylindrical, is supported at both ends, and a load is applied in the middle. The loading rate follows ASTM D790 or ISO 178 standards. If you look at the flexural strength test curve shown here, on the x-axis we have strain and on the y-axis we have flexural stress. For a brittle material, the curve rises steeply to a peak. That's the fracture point, and then drops sharply because the sample breaks quickly after reaching maximum stress. From this test we get two main outputs: flexural strength in megapascal and the modulus, which tells us the stiffness. Shear testing. Shear testing tells us how well a material resists sliding between its layers. This is done using single shear, double shear, or torsion shear methods. The specimen could be a plate, a fastener, or a laminate. The test follows ASTM D5379 or ISO 4585, where we apply a controlled displacement. If you look at the shear stress versus shear strain graph, you'll see that stress increases steadily with strain until it starts to level off, meaning the material is no longer able to take more shear load without significant deformation. From this, we determine shear strength and shear modulus. Testing.
Impact testing measures how tough a material is when hit suddenly. We commonly use the Charpy or ISO methods with a notched specimen following ASTM E23 or ISO 1481. The principle is simple. A pendulum swings, hits the specimen and breaks it. By measuring how much the pendulum's swing height reduces, we calculate the energy absorbed in joules. We also do temperature-controlled impact tests to see how materials behave during the ductile to brittle transition. From this test, we report the absorbed energy and note the fracture appearance, whether it's brittle, ductile or mixed.
Let's move on to hardness testing. The purpose of hardness testing is to measure how resistant a material is to localized plastic deformation. In simple terms, how well it can resist being dented or scratched. There are different methods for this. Brinell, which uses a large ball indenter giving us the HBW value. Rockwell, where we measure the depth of penetration and the result is in the HR scale. Vickers, using a micro indent giving us the HV value. For all these methods, we need a smooth, flat specimen surface, and we apply loads ranging from a few grams to several thousand kilograms. The final result is a hardness number, HBW, HR, or HV. Looking at the graph on the right, we see the hardness test curve. On the x-axis, we have the indentation depth in millimeters, and on the y-axis, the applied load in kilograms force. The curve shows that as the indentation depth increases, the load applied also increases. This tells us that harder materials will have smaller indentation depths for the same load. Now let's talk about fatigue testing. This is about evaluating a material's resistance to failure when it's subjected to cyclic or repeated loads. But importantly, these loads are below the yield strength. We usually test standardized specimens as per ASTM E466 or ISO 1099. The procedure involves applying a cyclic load, either stress-controlled or strain-controlled, until the specimen either fractures or reaches a target number of cycles. Some key parameters. The type of loading. This could be axial, bending or torsion. The stress ratio, which is the minimum stress divided by the maximum stress. Frequency, typically 10 to 100 Hz, but lower for precision or heat-sensitive materials. And the number of cycles to failure, which is used to plot what we call an SN curve. Now, if we look at the fatigue strength graph on the right. On the x-axis, we have the number of cycles, and on the y-axis, the stress. You'll notice that as the number of cycles increases, the maximum stress the material can withstand drops, but eventually it levels off. That horizontal dotted line is the endurance limit. Below this stress level, the material can theoretically endure an infinite number of cycles without failing. In real-world terms, hardness testing helps us choose materials that resist wear and indentation, while fatigue testing helps us ensure they can survive repeated use. Both of which are crucial in automotive, aerospace, energy, and structural applications. Torsion testing. This measures how a material behaves under twisting loads, basically its shear modulus, torsional strength and ductility. We use a solid or tubular cylindrical specimen, apply torque, and measure how much it twists until it fails. The graph here shows torque on the y-axis and angular deflection on the x-axis. A steeper slope means stiffer material. This helps us find shear stress-strain curves and modulus of rigidity. Now creep testing. This checks how a material deforms slowly over time under a constant load, especially at high temperatures. We apply constant stress to a standard specimen and measure strain over hours, months, or even years. The curve has 3 phases: primary, where the rate slows down; secondary, where strain increases steadily; and tertiary, where it accelerates until failure. It's crucial for materials used in turbines, boilers, and high-temperature components. Fracture toughness testing. Here, we want to know how resistant a material is to crack growth. The specimen already has a pre-made crack, like a CT or SENB sample, and we apply load while monitoring the crack's extension. The curve shows stress intensity versus crack extension. First, linear, then non-linear, and finally, instability where the crack rapidly propagates. This gives us values like KIC, which are vital for safety-critical designs. In short, torsion tells us twist strength, creep tells us long-term deformation at heat, and fracture toughness tells us crack resistance. As you can see in this table, these are the key ASTM and ISO standards that need to be followed for different material strength tests. For instance, flexural testing follows ASTM D790 and ISO 178 for specimen size and loading rate. Impact testing follows ASTM E23 and ISO 148-1 for notch type and striker speed. Hardness testing uses ASTM E18 and ISO 6508 with conversion charts between hardness scales. The same applies to the other test types listed here. This table acts as your quick reference for the standards to comply with. At November Services, we ensure your products meet global safety and performance standards through material strength testing and expert consultancy. We offer tests like tensile, compression, hardness, impact, fatigue, and torsion, as per ASTM, ISO, and BIS standards. Serving industries from automotive to aerospace, we provide accurate testing, certification, and failure analysis, backed by advanced equipment and detailed reports. Our services span testing, consultancy, engineering, product development, and research, helping you deliver products that are validated, compliant, and production-ready. Thank you for your attention. We appreciate the opportunity to share our testing capabilities with you. At November Services, we're committed to delivering precise, reliable, and standards-compliant testing, backed by expert consultancy. For inquiries, bookings, or technical support, feel free to contact us anytime. We look forward to working with you.